Alright guys, welcome back to our videos. In this one we're going to go over the test review for Units 1 and 2, the packet that we gave you last week. We're going to go through all the problems and give you the answers so that you can review for the test on Tuesday. Alright, so let's scroll down here to our first multiple choice problems. Let's see. So the first one says, what is the approximate width of a person's little finger? So when I look at problems like this, I like to just eliminate the ridiculous options first, right? So the width of my little finger, the width of my pinky, a meter would just be ridiculous. 0.1 meters, so a tenth of a meter, that doesn't seem so ridiculous, maybe at first, but 1/10 of a meter, if I sort of visualize a meter stick, that seems like a lot to be 10 centimeters, right? So that's maybe more the width of my palm, but not the width of my pinky, so I'll eliminate that one. 0.01 meters would be 1/100th of a meter, right? So 0.1 is a tenth, 0.01 would be 100th of a meter, or 1 centimeter, right? Centi means 1/100th of. So 1 centimeter doesn't seem so ridiculous, so I'll leave that one there for now. And then let's look at this last one, 0.001 meters. So that would be 1/1000th of a meter, or a millimeter, right? A milli means 1/1000th. And my pinky, I think, is definitely much larger than 1 millimeter, so I'll eliminate that choice number 4. And then that leaves me with the one that I thought might be reasonable, right? 1 centimeter, 0.01 meters. So the answer to our first one is number 3. Number 2, what's the approximate mass of an automobile? So again, we'll go through the same process. Look at the first one. 10 to the 1 kilograms, right? 10 to the 1 would just be 10. 10 kilograms. Now maybe you're not familiar with what a kilogram is, but a kilogram is about 2 pounds is what you can think. So roughly 20 pounds, I think an automobile, a car, is much more massive than that. So I'd eliminate that first one. 10 to the 2 kilograms, right? 10 squared would be 100. So 100 kilograms. That also seems like about 220 pounds if I consider that 1 kilogram is about 2 or 2.2 pounds. 220 pounds or 200 pounds is about the mass of a person, right? About the weight of a person. And people go inside of cars, so. And a car definitely has no problem carrying people around, and people definitely do have problems carrying cars, right? We can't do that. So this one doesn't seem to make sense either for a car to weigh about 200 pounds, about 100 kilograms. That doesn't make much sense. 10 to the third would be 1,000 kilograms, right? So roughly 10 times more massive than a human. That seems kind of reasonable, so we'll leave that one. 10 to the 6 kilograms. Now we're really jumping up, right? We did 1, 10 to the 1, 10 to the 2, 10 to the 3. Now we're going 10 to the 6th, so 1,000,000 kilograms. That seems like quite a bit. 1,000,000 kilograms would be about 2 million, over 2 million pounds. So, you know, that seems like quite a lot for a car, a lot for an automobile, so I'd eliminate this number 4. And I'd go with the one that seemed reasonable, number 3, 10 to the 3rd kilograms, right? 1,000 kilograms. So the first two, 1 is number 3, 2 is number 3. Let's take a look at number 3. The diameter of a United States penny is closest to what size, right? So again, we're looking in meters just like the first problem. 10 to the 0, anything to the 0 is 1. So 10 to the 0 would be 1 meter. A penny is definitely not a meter in diameter. That'd be huge. So we're going to eliminate that right off the bat. 10 to the negative 1 meters would be a tenth, right? This would be like our 0.1 from up here. A tenth of a meter. That seems kind of reasonable maybe again, but if we think back to the width of our finger problem up here, a tenth of a meter is 10 centimeters, which is maybe about the width of my palm. So a penny, I can fit a whole bunch of pennies in my palm, so that seems a little bit off also, so I'd eliminate that one. 10 to the negative 2 would be 0.01 meters, or about a centimeter, just like our little finger up here was, 0.01. That seems pretty reasonable for the size of a penny. I could rest a penny right on my pinky, right on my little finger, and it'd be about the same width, so I'll leave that one, and then I'll look at the next one. 10 to the negative third meters would be 0.001 meters, or 1/1000th of a meter, again, or like a millimeter. And a millimeter is much, much smaller than a penny, so I'll eliminate that one. And again, we're going with number 3. So 1, 2, and 3 answers are all number 3. Okay, let's see number 4. What's the approximate length of a baseball bat? So again, we'll go through this. 10 to the negative 1 meters would be 1/10 of a meter. 10 centimeters, that's too short. 10 to the 0 meters is 1 meter. That seems reasonable. I'll leave it. 10 to the 1 meters would be 10 meters. That seems much, much too long to be a baseball bat. 10 to the 2 is 100. That's crazy. That's the length of like the straightaway on a track. That's much, much bigger than a baseball bat. 1 meter seems pretty reasonable. Number 2. What's the approximate diameter of an inflated basketball? Okay, so now we've got our powers of 10, but we've got our base number, or our coefficient out front, right? All these 2's. So since all the coefficients are the same, I'll just ignore them and look at our powers of 10 again, right? So what's the approximate diameter of an inflated basketball? 10 to the negative 2 is 0.01, so that would be a centimeter. 2 times 1 centimeter, right? 2 centimeters, that's way too small to be a basketball. That's more like the size of a bouncy ball or something like that. 2 times 10 to the negative 1 meters. So 10 to the negative 1 would be 10 centimeters, 1/10 of a meter, right? And then 2 times 10 centimeters would be 20 centimeters. So that's about, a little bit less than a foot. 20 centimeters seems kind of reasonable. 2 palm widths, roughly. So I'll leave that one for now. 2 times 10 to the 0. 10 to the 0 is 1. Anything to the 0 is 1, so 2 times 1 would be 2 meters. That's much too big to be a basketball. And then 10 to the 1 is 10. Anything to the 1 is itself, right? So 2 times 10 is 20 meters. That's way, way too big to be a basketball. So let's go with number 2 here. About 20 centimeters. That's reasonable. Makes sense. Last multiple choice, right? Number 6. The length of a football field is closest to... Let's see, now we have not all in the same units, right? All these other problems, we had meters, 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 kilograms, 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 meters, 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 right? Now we've got centimeters. dm is decimeters, which is actually 1/10 of a meter. That's what we've been talking about when we're doing the 10 to the negative 1s, right? These were all 1/10 of a meter. So a decimeter is a 1/10 of a meter, or 10 centimeters. Kilometers are really long and millimeters are really small. So 1,000 centimeters, there's 100 centimeters in 1 meter stick. So that would be like 10 meter sticks long. I think a football field is much longer than that, so I'll eliminate this one. 1,000 decimeters would be 1,000 times 10 centimeters. So let's think about that one a little bit, right? So if I had 1,000 meters, that would be a kilometer. That would be much too long to be a football field. But I'm talking about tenths of a meter. So 1/10 of a kilometer would be 100 meters. So this is equivalent to 100 meters. And that seems kind of reasonable, right? The straightaway on a track is about the length of the football field when the track's going around the football field. So, and the straightaway on a track is about, right, 100 meters long. So if this is 100 meters, that seems like a reasonable choice. Let's look at the other two. 1,000 kilometers. 1,000 kilometers is really, really, really long. That's way too much to be a football field. 1,000 millimeters is only 1 meter, right? There's 1,000 milli. The milli is 1,000th. There's 1,000 millimeters in 1 meter. This is only 1 meter. That's way too short. So 100 meters, or 1,000 decimeters, makes sense. So number 2 for question 6 there. All right, let's take a look at these conversions. 9 centimeters into millimeters. So in every 1 centimeter, right, if I think about a meter stick, looking at a meter stick, or I think about looking at the metric edge of a ruler, in every 1 centimeter there's 10 millimeters. So if I had 1 centimeter, the answer here would be 10. But I have 9 centimeters, so I have to multiply 9 times 10 So there's 90 millimeters here. Number 8, okay, now for the 7 we went centimeters to millimeters, now we're going to go the other way, right? For 8 we're going millimeters to centimeters. So here I figured out how many millimeters were in 1 centimeter and multiplied. Here we're going to kind of go in reverse. So for every 1 centimeter, there's 10 millimeters in there. So if this said 10 millimeters, I would know I'd only have 1 centimeter. But we have 70 millimeters, right? So I have enough millimeters to make up 7 whole centimeters. Number 9 is 400 centimeters into meters. Smaller into bigger again, just like number 8, smaller into bigger. In a meter, I know there's 100 centimeters. So I have at least enough centimeters to make up 1 meter, but I actually have exactly enough to make up 4. So I have 4 meters if I have 100 centimeters. And now small to big again, we have 3,000 meters in a kilometer, right? If we take a look at our Regents reference tables and we look at the metric prefixes, the kilo means 1,000. So kilometer means 1,000 meters. So in every 1 kilometer, every 1 kilometer is 1,000 meters, but I have 3,000, right? I have 3 times that many, so 3,000 meters is 3 kilometers. All right, let's take a look at the next page here. This first page was all on sort of metric estimation and physics skills, right? Our first unit. And as we get onto this next sheet, now we're talking about motion, right? Unit 2. So, number 1, considering the following position versus time graph, right? So we have position on the y-axis, time on the x-axis. Determine the average velocity of the object. Average velocity is the first thing I'm looking at here, right? The fact that they want a velocity and not a speed. So again, I have to think about velocity being a vector, right? V's, vector velocity. And I also know that the position vector that goes along with velocity is displacement. So my average velocity is always going to be equal to my change in displacement, this d is displacement, right, over time. So what I need to figure out is how far does this thing go in how much time, right? It's displacement over how much time. So I can look at, let's take a look at this line. So it looks like, you know, maybe this first box looks okay, but if I look a little further, it's not quite crossing there. It's definitely not crossing here. It's not quite crossing there. Crosses here again. So actually what I'm going to do is I'm going to look at the change in y all the way up and the change in x all the way over, right? This is my change in x, change in y over here. So my change in y, which is my delta D, right? I go 60 down to 10 is a change of 50, and my unit was meters, right? I got that off the y-axis label. So 50 meters is my delta D, my displacement, and how much time does that happen over, right? So now I go 1, 2, 3, 4, 5, 6 boxes, and every 1 box is a second. So 50 meters over 6 seconds. Let's see, that comes out to be about 8.33 is what it should be. 8.33 meters per second. 8.33 repeating, really. But you can round. Really, actually, I shouldn't do that. I should round to 2 or to 1 sig fig, really, right? So I've got 2 sig figs for my velocity or my position number here and only 1 here. So I can really only go down to 1 sig fig. So I'm going to write down 8.33 because that's what I would calculate. But if you were using correct sig figs, this would just be an 8. Write a mathematical model to describe the motion of the object. Okay, so anytime we're asking about a mathematical model, we're talking about an equation, right? Mathematical model, that's an equation. So whenever you see that, you should think, I need to write an equation down. And if I'm writing an equation that describes the motion of the object, I want an equation that describes its position. So if x is our variable for position, I want to do x equals, right, position equals. And then to decide what goes over here on this side of the equation, I just look at what my motion looks like on the plot, right? And this definitely looks linear. So that tells me that what's going to go over here is the equation for a linear relationship, equation for a line, right? Y equals mx plus b. So my position is equal to my slope. The slope was what we got up here, so 8.33 meters per second. And it is important that I keep the units in here, right? You should always have the units on whatever numbers you're talking about in the equation. 8.33 meters per second. And my format is y equals mx plus, right, plus something. So I've got my m. This is going to be time, t, I'll put in. And then plus what? This is always the y-intercept over here, right? So I have to go back over here and look at what my y-intercept is. It looks like it's 10 meters, so I'm going to plug in 10 meters, and again I'm putting the unit there. So this is, and I'll just erase this line, make it a little bit cleaner, but this is our equation or our mathematical model for the motion of that object. Alright, let's take a look at number 2. And I'll switch colors here to an orange. So, describe the motion of this object. So what I always like to do with these is first look at the time periods of the things that change, right? So in my first time period, this, first of all, this is a velocity versus time plot, right? The last one we were talking about position versus time. Now we got to take note that we're talking about velocity versus time, so we got to think about this a little bit differently. In the first 2 seconds, right, 1, 2, I've got this flat line at 4, which means that for 1, 2 seconds, this object was traveling at 4 meters per second. So I'm just going to write down 0 seconds to 2 seconds. And then I'm going to say constant velocity, but it's constant positive velocity, so I'll write down positive velocity. And then I'll just write 4 meters per second over here, so that, because I can get that bit of information. I could have also written constant positive 4 meters per second velocity, something like that. Just, you want to always, whatever information you can pull out of these plots, right here. I mean, you might write one piece of information like constant velocity, but that's not quite enough. You want to tell us that's positive and tell us the total value for it, right? The magnitude. For the next time period, I'm going from 2 seconds to 3 seconds. So I'll write 2 seconds to 3 seconds is my next bit. And now it's doing something different, right? Now I've got a flat line down here at -3, right? This part here is -3. So this is constant, also constant velocity, right? Because it's a flat line, but it's constant negative velocity this time. And it's at -3 meters per second. That's how fast we're going in that second time period. Now we've got one last time period to look at, and I'm just going to put it up here because I'm running out of space. But we've got 3 seconds to 5 seconds. Let's take a look at what's going on with that line. Now that's also a flat line, constant velocity at 0. So I can say constant 0 velocity, right? And if I have 0 velocity, I should also kind of say what's really going on there. The object's not moving, right? It's standing still, something like that, right? Something like that. So I'm going to write constant 0 velocity, not moving, from 3 to 5 seconds. Okay? All right, let's look at B. Find the distance traveled for the 5-second interval. Now the thing I want to note here is distance, right? Up here in the last problem we were talking about velocity for this problem, right? And I picked out average velocity to guide me in what I did mathematically. This time we're talking about distance. So I need to do something a little bit different to figure out the distance traveled in the 5-second interval, right? So what I want to do from here is look at how fast did it go in all its time periods, which is what we did in part A, and add up the distance it covered for all those time periods. But I've got to figure out what that distance is for each time period, right? So for 0 to 2, it went 4 meters per second, right? And think about this. If it had just gone to 1 second, and I said it's going 4 meters per second for 1 second, you'd tell me that it traveled 4 meters. Its distance is 4 meters because it went 4 meters per second and it only had 1 second to do it in. But it actually had 2 seconds, so it's 4 meters per second times 2 seconds, right? And our seconds cancel, which gives me 4 times 2 meters, which is 8 meters. And I'm just going to leave that, and I'm going to put it in absolute value bars. And the reason I'm doing that is because, again, we're talking about distance, right? I don't care what direction it traveled in. I don't care if it went out, came back to where it started. I just want to know, how, if it's a person walking, what did their legs feel? Not how far did they get from their starting point. That would be displacement. That looks like what we're doing in the next one. So the absolute value bars will make sure that it always just gives me a magnitude, right? It gives me the amount of the number that I'm calculating. So this is our 0 to 2 second calculation. Now we need to add, also in absolute value bars, our 2 to 3 second calculation. So from 2 to 3 seconds, it was moving at -3 meters per second, and it was doing that for 1 second, right? So it moved, it went -3 meters in that 1 second. But this is where the absolute value bars really come in, because I don't care that it went back if I'm just talking about distance, right? This negative means that it went out at 4 meters per second for 2 seconds, and then it went back towards where it was at -3 for 1 second. But I don't really care about that for distance. I just care how far it traveled. So that's where my absolute value bars come in here, right? This is going to give me a 3 meters because my seconds cancel. And then for the last part, just for consistency, we'll do the last part, even though I think you can probably guess what's going to happen. For the last part, we're going 0 meters per second. And we're doing that for 2 seconds, but it really doesn't matter how long we're doing that for because we're not moving, right? Seconds cancel, just 0 in here. This whole thing is just 0. So what I've got here is 8 meters plus -3, but in absolute value bars is 3 meters, and then the 0 meters I don't need, right? So 8 plus 3 meters is 11 meters. So the distance traveled here was 11 meters. Okay, part C. Find the displacement of the object and explain how we arrived at that answer, right? Now we could explain, if we do this mathematically, we can explain, our explanation is in our math, because we'll see how we did it. We just don't want to write down a final value and not have any work to show. So find the displacement of the objects. Last time we found the distance, now we're talking about displacement. And I can reuse some of the numbers that I came up with up here in this part, right? So for distance, I just cared about how much ground the person or the object covered while it was moving around, how much it felt like it moved. But displacement, I'm talking about how far it is from its starting position. So the first thing it did was travel out 8 meters, right? We got that part. It was positive. Now, we don't keep any absolute value bars. I just subtract this 3 meters from here because it went back at -3 meters per second for 1 second. So it turned around and went back. So I've got 8 meters minus 3 meters comes out to 5 meters. That's our displacement. And you'll notice that the displacement is different than the distance. It's less, right? I ended up not so far away from my starting position, but I walked around a lot. Alright, so let's take a look at part D here. Draw a corresponding position versus time graph and number the axes. You may assume that the object starts from the origin. Okay, so we're doing this from the velocity versus time graph up here. So the way that I want to do this is, right, if I was going the other way, let's take a look back at the first one. Now this number 2 question does not correspond with this at all. And I think you probably guessed that, but let's just take a look at this because this is a position time plot like the one we need to make. This gave us the position at any time, and our slope of our line is our velocity, right? That's how we figured out this 8.33 meters per second. So when I'm going backwards from a velocity time plot to make a position time plot, I want to pull the numbers from the velocity time plot and make them into slopes on my position time plot. So first let's label all the axes, right? Down here is going to be 0, and this is also going to be 0, and then I'm going to just go 1, 2, 3, 4, 5, 6, 7 seconds on the time in seconds on the x-axis. And then let's see, let's do 1, 2, 3, 4, 5, 6, 7. We can go up to 8 on our y-axis for our position in meters. So for the first 2 seconds, right, for these first 2 seconds on this graph, I can look at my velocity plot and say, okay, the slope that I want to plot here is 4 meters per second, right? I want to go up 4 meters in 2 seconds. And what I'm going to do is up 4 meters for the first second, right? That's what I would get here, 4 meters in 1 second, and then total are 8 meters in 2 seconds. So I get all the way out to 8 meters in 2 seconds, which corresponds to what we got before. We traveled 8 meters in our first 2 seconds. So that's perfect. So that's our first leg. Now our second leg, we've got -3 meters per second for 1 second. So I lost 3 meters in 1 second. So I've got to go down 1, 2, 3 and over 1 to the 3 seconds, right? That's our next leg. And then for our last leg from 3 to 5, right, this is going to be my end point right here. We didn't move at all, right? We had 0 velocity, which means we just stayed right at 5 meters. So my last leg here is just a flat line. And that's what our position time plot would look like based on our velocity time plot. And now let's see if we've got to answer a few different questions about it, right? So, question E here, part E, is find the average velocity based on this plot from 0 seconds to 5 seconds. So average velocity, the easiest thing, just like in the first problem we did before, right, just like back here, average velocity, the easiest thing to do is always just do the change in displacement over time. So I can look at my change in displacement over time, and I'll see that my change in displacement was 5 meters, right? My total, whatever I got out to, as far as I got in the end from my starting position was 5 meters. That's my displacement. And the time that it took me to get there was 5 seconds, right? I got out to 5 seconds, 5 meters. So that's just 1 meter per second. That's my average velocity based on this plot. Okay, let's find average speed now, right? Now we're looking for average speed from 0 to 5 seconds, the same time interval, and explain how we got our answer. We can do that with the math. So average speed is going to be, our average velocity was our change in displacement. But our average speed, I'll do S bar, right? We did velocity average, I'll do speed average, is change in distance instead of displacement over time. And that's going to be different than 5 meters, right? And we actually got that way back up here. The 11 meters was the distance that we said we traveled. So I'm going to put down 11 meters for the distance, our change in distance. And our time was 5 seconds again. So this comes out to about, let's see, so 10 divided by 5, right? This is going to be the same thing. I'll do this out actually for you. So this is the same as 10 divided by 5 plus 1 divided by 5, right? I can break that fraction. You can do this in your calculator, but I think it's good to try and do this math mentally and out by hand sometimes, right? 10 divided by 5 is just 2. And then plus a fifth, right, is 2. And then 1 divided by 5 is 0.2. So 2 plus 0.2 is 2.2 meters per second for my average speed. Now you don't need to do this out by hand. You can just plug in, 11 divided by 5 in your calculator and you'll get 2.2. I guarantee it. But I like to show out, how I would do that in my head or by hand, because it's convenient when you don't have a calculator to do that. Okay, number 3, let's switch colors again. I'll do a nice hot pink this time. A bird travels towards the origin and then suddenly reverses direction. And that's what we've got the plot, position versus time here for. Right? Now we want to find the average velocity from 30 seconds to 40 seconds. So I want to go from 30 to 40. So this part here, just this downslope. So my average velocity, again, is my change in displacement over time. So if I look at my change in displacement, I'm going from 30 meters down to 10 meters. So I'm going 30 meters, and I'm going, sorry, I've got this backwards, right? So I'm going negative 20. I'm losing 20 meters, right? So I went from 30 down to 10. So my displacement is negative 20 meters back towards wherever I was coming from, right? And then the time that I did that in is not 2. It's not 2 boxes. It is 2 boxes, but it's not 2 seconds. It's 30 to 40, which is 10 seconds. So negative 20 meters over 10 seconds would give me negative 2 meters per second. So that's my average velocity, the bird's average velocity, from 30 to 40. Okay, B, we're going to find average velocity again, but this time from 40 to 50. Let's do that in a different color. Let's go back to blue. So now we're going 40 to 50. And we have to look at our change in displacement again, right? Delta D over T. So the change in displacement this time, you guys probably caught that mistake faster than I did. Should have gone out to here, right? 40 to 50. Let's see, we go from 10 out to 20, so we're going positive this time. And so that's 10 meters change in displacement. And then the time that we're doing that in is 10 seconds, right? 40 seconds to 50 seconds. So that's 1 meter per second. Okay, let's see. Determine the average speed from t equals 30 seconds to 50 seconds. Okay, let me get a new color. Let's do green this time. So now we're doing like the whole graph, right? 30, see, I'm doing it again. 30 out to 50. Average speed this time, though, not velocity. So this is going to be, average speed is going to be my change in distance, not displacement, because we're talking about speed over time. And so the first time my change in displacement, we said, was negative 20 meters. But for distance, that's the same as saying 20 meters, right? Because distance, I don't care about what direction I went in. I just care how far I went in whatever direction. So I can say 20 meters, that's 30 to 40. And then 40 to 50 we said was 10, right? Also, doesn't matter what direction I went in, doesn't matter if it was positive or negative for velocity. For displacement, I just care about the magnitude, how far I went. All right, so 20 and 10 meters, 30 to 40, and then 40 to 50. And then the time is 30 to 50, so that's 20 seconds. So we're going to have 30 meters over 20 seconds, which is 3 over 2, which is 1.5 meters per second. Again, you could plug that in your calculator. I'm doing it out by hand. Either way works. All right, part D. Now we're talking about what we thought we might have been for C. So velocity, this time we're back to velocity. So my average velocity is my change in displacement over time. Now we're talking about my negative 20, right? I've got to put my negative 20 in from up here. That's the first leg. Displacement was negative 20 plus 10 meters for that second leg, positive displacement that time, over a 20-second time interval. So now I'm going to have negative 10 meters. You can see how this is turning out different than the speed, the average speed. Negative 10 meters, right? Negative 20 plus 10 gets me negative 10 over 20 seconds is going to be negative 1 meter over 2 seconds, right? I'm just canceling these zeros. That's what I did up here without showing it to you explicitly. Negative 1 over 2, that's going to be negative 0.5, or you could leave it as a fraction 1/2. But it's got to have the negative because we're talking about velocity this time, right? Negative 1/2 meter per second. All right, our last problem here. Find the velocity at t equals 35 seconds. At t equals 35 seconds, right? So right at that spot. So let's go find that, and we'll do it in red, right? For this last one. Right at 35, so this is 30, this is 40, this must be 35. Right there, what is my velocity? Now this is a position versus time plot, so my velocity is my slope, whatever it is. So if I'm talking about a velocity at a specific time, I'm just talking about what the slope is at that point. And since this is a constant slope over this entire 30 to 40 second time interval, right, this entire downslope, I already know that any point on here is going to have the same velocity, the same slope. So, and we found what that was before, right? We did that first. The average velocity from 30 to 40, which is this, was negative 2. So at 35, right in the middle, it's just going to be negative 2 meters per second. And I might want to write a note down that I just said, you know, the way I figure that out is slope at 35 seconds, right? That would be enough to tell whoever's grading this that you looked at the slope here and you said, okay, I know that there's constant slope. It must be the same as what we were talking about before. Negative 2 is my answer. All right, guys, I hope if you watched this that it was helpful. If you have any more questions, we might take a couple, quick minutes right before the test on Tuesday. But I hope this was helpful, and good luck reviewing if you're doing any more. Have a good night.